So welcome to another Advanced Higher Chemistry video. We're still on Unit 1 and this video is talking about transition metal complexes, which are a new type of compound or material to Advanced Higher, and you're going to learn about a new type of bond and names that we give to the components of transition metal complexes. So a transition metal complex is going to be drawn a bit like this, and it will only have those square brackets on it if it is charged. And the charge, you can see the charge is drawn on the inside of the bracket here. However, it is more common for the charge to actually be drawn on the outside of the bracket. So I've copied this image off something else. If you're doing your own one, please make sure that you put the charge outside of the square bracket. Now, when we look at this transition metal complex, we can see that right in the center, we've got a transition metal. In this case, we've got cobalt. And then we have got different groups bonded around it. And we typically have these groups bonded in an octahedral pattern. They do not have to be octahedral, but at Advanced Higher, they're always going to be octahedral. So the transition metal is at the center. That is the only place you're going to find the transition metal, is right in the middle. And then around the outside, the things that are bonded to the transition metal are called ligands. Now, a ligand can be a negative ion. It could be something like chloride, fluoride, even oxide. But it can also be neutral molecules. So in this image here, we've got ammonia. Ammonia has no charge. And ammonia and water and carbon monoxide are going to be three neutral molecules that you may see on a transition metal complex, and they surround the metal. Now, between the ligand and the transition metal, we have bonds. These bonds are different to other types of bond that you've seen so far. Our ligands have non-bonding pairs of electrons. So if you do not have a non-bonding pair of electrons, you cannot be a ligand. So for example, methane cannot be a ligand. You must have a non-bonding pair of electrons. And the ligand shares both of those non-bonding pair of electrons with the metal. So rather than have a covalent bond where each atom involved in the bond is sharing one electron each, we've got a new type of bond where one of the atoms is sharing two electrons and the other atom is not sharing any electrons. So there's still only two electrons in the bond, like a normal covalent bond, but both of those electrons have come from the same atom. And we call this one-sided sharing of electrons a dative covalent bond. So a dative covalent bond is a covalent bond where both of the shared electrons have come from one of the atoms. And you're going to see them in transition metal complexes. So there are a few common ligands that are involved in transition metal complexes. These are the most common ones, but in the next slide, when we look at naming, in the next video, when we look at naming transition metals, we will see that there are a few more that we would add to this list. These are just the most common ones. So we have things like water. Now, water is going to bond through the oxygen because it is oxygen that has the non-bonding pair of electrons. Cyanide is a negatively charged ion and it will bond through the carbon. So make sure if you're drawing a bond between a ligand and a transition metal that you're putting the right part of the molecule pointing towards the metal. In water, oxygen. Cyanide, carbon. In ammonia, it is the nitrogen that has the lone pair, so it's going to be bonded through the nitrogen. Hydroxide through the oxygen. And then with chloride, fluoride, and bromide, and even iodide, it's only one atom, so it's bonding through that atom itself. Now, these ligands can only form one bond, and they get called monodentate. Mono means one. Dentate actually means teeth, and it is because we sometimes describe transition metal complexes as the ligands biting onto the transition metal. So these ones, when they bite, they've only got one tooth to bite with. So they're only going to form one bond. Not every ligand will form one bond. Some are capable of forming more than one. So we've got this ligand here, which you can see has got two carboxyl groups on it. That is oxalic acid, or in this form where it's ionized, it's known as oxalate. It is bidentate. It can make two bonds. And those bonds are actually more likely to come from the O- ions on that ligand rather than the double bond oxygen ones. So two different bonds. The bonds can be drawn as solid lines or as hashed lines shown here. But because it can form these two bonds, it is bidentate. It has two teeth. Now, denticity is the number of bonds to a metal that a ligand can make. Most ligands are going to be monodentate. There will be a couple that are bidentate, but you can go all the way up to hexadentate. And you will need to know this one, EDTA. You don't need to know what it stands for. If you really want to, it's ethylene diamine tetraacetic acid. It has 6 positions in which it can bond. So the 2 nitrogens in the middle each have a lone pair of electrons. And when the carboxyl groups have the protons, the hydrogens removed, it's going to have 4 oxygens capable of forming dative covalent bonds as well. So when it bonds, it actually bonds like this. 2 bonds from nitrogen and 4 bonds through oxygen, giving it a total of 6 bonds. EDTA is a common ligand used in titrations for working out the concentration of transition metals because it bonds in a 1-to-1 ratio. So if you know how much EDTA you've used, you know exactly how much transition metal there is in your solution. You can work out the denticity of a ligand by looking for every atom that has a lone pair of electrons. You're typically looking for nitrogens and occasionally oxygens. For every nitrogen it has, unless that nitrogen has a positive charge on it, it's going to form one bond. So how complexes are written and drawn? So complexes are drawn with a square bracket around the whole thing. That just lets you know that is a complex. And that square bracket is whether you're drawing a diagram or whether you're writing it out as a formula. Square bracket is indication that it is a transition metal complex. For the complex, the metal is usually written first because it is positive, and we tend to go positive things, then neutral things, then negative things. But just conventionally, you're usually going to see the metal first, then the ligands, and then your brackets. If there is a charge, the charge goes on the outside of the square bracket. And our diagrams will also have square brackets drawn around them. And again, with charge, you can either write the number, then the charge, or the charge and then the number. So you can see on that one on the left, it's written +2. You can write 2+, normal convention for charges, and 2- or -2. Now, coordination number is related to denticity. Coordination number is a feature of the metal rather than the ligands though. It is the total number of dative covalent bonds around a metal. And you're usually going to be given a diagram of a transition metal complex and asked to work out the coordination number. It is literally a counting exercise. However, sometimes you may have to do it from a complex, from a formula. And what you need to be able to do is work out what the denticity of each ligand is, then how many of each ligand there is to work out the coordination number. So in that first complex, iron with 2 chlorines and 2 cyanides. Chlorine and cyanide are all monodentate. So we've got 4 monodentate ones, which means the coordination number is 4. This nickel one, OX, is the symbol for oxalate. Now oxalate was bidentate, and we have 3 oxalate ligands, which means that's 6 bonds to the nitrogen. And so it's got a coordination number of 6. Now in typical examples that you would have to draw, the coordination number has a maximum number of 6. However, if you are given a diagram and you can see the bonds, that coordination number can go as high as 12, and you're just going to have to count them. So this has been our introduction to transition metal complexes. In our next video, it is going to be the tedious task of working out how to name a transition metal complex, and there are quite a few rules you're going to have to learn for that.